In today's lesson, we will be talking about exponential growth and decay, and we'll be relating that concept to real-world scenarios. Before we begin, let's first talk about what exponential growth means and review about the exponential function. First, the general form of an exponential function, y equals a times b to the power of x. So the a in our equation, when we're talking about story problems, we'll refer to the initial amount, how much are we starting with, and then from there it will be either increasing or decreasing. And just a little side note, a is always greater than 0. And that is for exponential growth, because if it was negative, then we wouldn't have growth. And then b is the growth factor, usually the percentage that something is increasing. And for it to be growth, the b value has to be greater than 1. And I just want you to write down on a little side note, and this will make more sense once we start a story problem, but if we are working with growth, to find our growth factor when dealing with percentages, we will always be doing 1 plus whatever the percentage given is. In other words, if there is a 2% growth factor, 2% as a decimal is 0.02, but we would do 1 plus 0.02 because you have to add 1 in order for the growth factor to be greater than 1. Alright, let's do a few story problems using exponential growth before we do anything with exponential decay. Here it says, suppose your community has 4,512 students this year. The student population is growing 2.5% each year. Write an equation to model the student population. And then, what will the student population be in 3 years and 10 years? So first we need to write the equation. Y equals a times b to the power of x, and we need to figure out what numbers go in for a and for b. Well, a is the starting amount, so how many students did we start with? 4,512. And then b, it's increasing at a rate of 2.5%, but b has to be greater than 1, so we're going to do 1 plus 2.5% as a decimal, 0.025, which equals 1.025. So, to write my equation, y equals 4,512 times 1.025 to the power of x. So there's my equation, and now to answer the questions, how many students will there be in 3 years and 10 years? That is what we will do. We'll use those numbers to evaluate, as x will represent years gone by. So for 3 years, just plug in 3 for x, 4,512 times 1.025 to the power of 3. Follow order of operations, and what do you get? You should get 4,858.9, but we're talking about people, so we'd want to round to the nearest person, which would be 4,859 students after 3 years. Now let's do that same thing, but with 10 years. So plug 10 in for x and then follow order of operations. In 10 years, if that rate of increase is consistent, the community will have 5,775.7 students, but let's round to the nearest student. So 5,776 students. Alright, here's our other exponential growth story problem. Suppose you invest $1,500, $1,500 into an account, and it's paying at a 4.75% annual interest. Find the account balance after 25 years. And once again, I want you to write an exponential equation in this form first, and then use that equation to solve the story problem. So, A is your starting amount. How much money are you starting with? $1,500. And B, the percent is 4.75%, but we're investing, so we want our money to grow. So we need to do 1 plus 4.75 as a decimal is 0.0475. If you ever get stuck on how to write your percent as a decimal, just remember you can always take your percent and just divide by 100, or move the decimal place twice. So, writing our equation, y equals $1,500 and 0.04. Oh, whoops. I just made a mistake. I forgot to finish adding 1. This should be 1.0475. So in my equation, it needs to be 1.0475 to the power of x. But we're going to plug in 25 to represent how much money will you have in 25 years. And you should get that in 25 years, you will have $4,785.66 in your account. Alright, now moving on to exponential decay, which just means we are decreasing exponentially. So, same equation, y equals a times b to the power of x. And just like in exponential growth, a represents your initial amount, how much we start with, and a is always greater than 0, so no negative values for a. And then b represents your decay factor, your percentage that you're decreasing. And remember, b has to be in between 0 and 1 in order for it to decay. So when we are dealing with decay and we're dealing with a percentage of decrease, you need to, instead of 1 plus your percentage, it would be 1 minus your percentage. So if you're decreasing at a rate of 3%, you would do 1 minus 0.03, which is 0.97. So that would be your decay factor. Alright, so here we have a story problem using exponential decay. A $30,000 purchase decreases 15% in value per year. Determine the value of the purchase after each of the following, 1 year and 3 years. So we want to write an equation and then use the equation to evaluate the question, finding out the value after this amount of years. So if you think about like a car depreciates over time. So this would maybe be a good example of maybe you're buying a car for $30,000 that's decreasing 15%. So to write the equation, y equals the initial amount, A, is $30,000. And then B is the decay factor, so 15%, but remember we have to do 1 minus 15% as a decimal is 0.15, which equals 0.85. So my equation is y equals 30,000 times 0.85 to the power of x, And now, to solve these, we just have to plug in 1 for x and then plug in 3 for x. So after 1 year, the purchase is now only worth $25,500. And then after 3 years, it is worth $18,423.75. Alright, last example using exponential decay, but this is a special scenario. It's involving half-life. So maybe circle or highlight half-life because this is kind of a special scenario in which we use exponential decay. So carbon-14 has a half-life of 5,700 years. That means the amount of carbon in an item is going to be cut in half every 5,700 years. Scientists use this fact to determine the age of things made of organic material. So this is how we find things, we find fossils, and we can determine how old they are. And it's based on how much carbon-14 is left over in that material. So, suppose the average page of a book containing 0.5 milligrams of carbon-14 is put into a time capsule. How much carbon-14 will each page contain after each of the following number of years? So how much carbon-14 will the page contain after 5,700 years and after 11,400 years? So we're going to write an exponential equation. Now, how much carbon-14 did they start with? Each page contains about half a milligram. So it starts out with half a milligram of carbon-14. And now the decay factor in every question involving half-life, your decay factor is always 1/2. Things will be cut in half. And then number of years, this is the tricky part. You are not plugging in 5,700 or 11,400 in for x. You need to figure out how many half-lives occur in that amount of years. So 5,700, there is 1 half-life in that many years. And then in 11,400 years, there are 2 half-lives. So you're plugging in 1 and 2 for x. So my equation, y equals 0.5 times 1/2 to the power of 1, and y equals 0.5 times 1/2 to the power of 2. So after 5,700 years, the carbon-14 is cut in half once, which would leave you with 0.25 milligrams. And then 11,400 years, the carbon-14 will be cut in half twice, and there will be 0.125 milligrams left over. So there's your full lesson on exponential growth and exponential decay with a special scenario of exponential decay involving half-life. So good luck!